All right. So this year, 2015, we celebrate the 25th birthday of Hubble. Can y'all believe that? I can say y'all, right? I'm in Texas. Woohoo! I'm from Arkansas, so I grew up saying y'all, and then I moved to DC, and people look at me weird, but I'm back in Texas, so I can be myself. Okay, Hubble, 25 years in space. That is hard to believe, right? Hubble has, in no small way, completely changed the way that we think about the universe. It's changed the way we understand the universe. From everything from things in our own solar system to the most distant reaches of the universe. And not only that, Hubble's had a huge impact on our culture. So more than just being a cool tool for scientists, Hubble has invaded our culture in a whole bunch of cool ways. I mean, people make stuffed Hubbles, for heaven's sake. This is on Etsy, for real. You can buy a stuffed Hubble with cute little astronauts. So, yeah, my birthday's coming up in a couple months. I love this thing. This is so cool, right? So Hubble has invaded our world in a good way. And so I can't give a talk about Hubble without showing beautiful Hubble images. So this is the ooh and ah part of my talk, all right? Saturn with Aurora. Ooh. And then Jupiter with its awesome red spot. Ah, yes. Okay, you don't have to keep doing that. But we're going to go a little farther out in the universe, and outside of our own solar system, we've also been able to explore star-forming regions within our own galaxy. So that's what this is a massive region of dust and gas where stars are being born. And then the very famous pillars of creation. So there are tiny baby stars being born in these dark pillars. And after stars live out their lives, they blow away all that dust and then they shine forward in beautiful star clusters like this. After stars go on for a while and live, sometimes they blow up like crazy, like this guy. It's the Butterfly Nebula. This is what happens to some stars at the ends of their life. And then, of course, in addition to cool things in our own galaxy, there are other galaxies as well. So this is an example of a nearby spiral galaxy, Messier M101, for those of you that need to know which Messier object this is. So this galaxy looks similar to what our own Milky Way galaxy would look like if you could get outside and look back on it. Of course, we can't do that, but we can study what the stars in our own Milky Way look like in order to figure out what kind of galaxy we live in. And we know we live in a spiral galaxy. In fact, lately we think we probably live in a spiral galaxy that has a bar. So this is an example of another galaxy fairly nearby that has a big bar in the center. Sometimes galaxies get too close to each other and they smash into each other. And that's a really cool process that you see going on here. So this is the antenna galaxy. So this is where two galaxies have come together and collided. This is a really cool process in the universe. I'm really interested in my own research in these sorts of galaxies that are merging or interacting. So we think that this is one of the primary ways that black holes grow throughout the history of the universe. So really, really fun things going on when galaxies get too close to each other. So galaxies also often gather together in groups and clusters. So this is an example of a galaxy cluster. And every point of light you see on this sky here is pretty much a galaxy. And so these galaxies are packed really tightly together in the sky, relatively speaking. But what you don't see here is a massive amount of dark matter. So in addition to all the bright lights you see, there's even more matter in the form of dark matter here. And what happens when we have all this dark matter in one tight space? We get a really cool trick of physics that allows us to do this thing called gravitational lensing. So if you look close here, you're going to see these little blue kind of strips all around. And this crazy guy here, I'm going to zoom in on it. Hopefully. There we go. All right. So check this out. I'm going to blow your mind here. So see this pink galaxy? So this is actually a distant galaxy behind the galaxy cluster. And the light from this galaxy as it passes through the mass of the cluster has been stretched and bent and magnified by the mass of the cluster. So this is gravitational lensing. This is general relativity in action, and we can see it in galaxies. So how cool is that? Really cool trick of physics that allows us to see distant galaxies in detail. So that's what we have going on here. Now, of all the awesome Hubble images that we've been able to see over the last 25 years, if I had to pick a favorite, this would be it. This is the Hubble Ultra Deep Field. And if you guys haven't seen this in detail, go online and look at it, because even projected here on this good screen and this good projector, you can't see the detail. But basically, every single point of light you see here, pretty much every point, there's a star, but almost everything else is a galaxy. And what the cool thing about this image is it's a tiny piece of the sky. So if you like stick your thumb up, you could cover up this point of sky, right? It's a little tiny patch. And in this tiny patch of sky, Hubble sees 10,000 galaxies. So it starts to tell you how big the universe is, right? Thanks to Hubble, we now know that there's something like a couple 100 billion other galaxies outside of our own galaxy. So the universe is vast and it's amazing, and I love this image. This is the image I ended up doing a lot of my dissertation research on when I was in grad school. So that's Hubble. Hubble's awesome. Woo! So 25 years now we've had Hubble. And it's done all this amazing science, and it's still going strong. So we're still using Hubble today. It's doing great work. After the last servicing mission in 2009, it's better than ever. So we're hoping Hubble lasts until 2020, maybe even a little bit longer. But from a scientific standpoint, there are a lot of ways in which we've pushed Hubble to its limits. And so we at NASA, of course, are building a new telescope to answer the biggest questions in astronomy today. So that's what I want to spend the last few minutes talking about.
Under construction is the premier telescope of the next decade. A next-generation space telescope designed to cause yet another giant leap forward in our understanding of the cosmos. It will carry some of the most advanced technologies ever placed on an orbiting observatory.
18 articulated mirror segments, 2.75 times the diameter of Hubble's primary mirror. Microshutters, wavefront sensing and control subsystem, 12 by 18 meter, 5-layer Captain-based sunshield.
The Webb telescope, a revolutionary tool able to study every phase in the history of our universe.
The Webb telescope.
That was really loud. Hope y'all can still hear back there. All right, so that's what's next. Very dramatic, right? It is really dramatic. This telescope is going to be amazing. And since we're building it to be the scientific successor to Hubble, I like to tell people kind of what the differences are. So the first big difference between Hubble and Webb is just the size. Okay, so when it comes to telescopes, size matters. And Hubble is about the size of a school bus. This telescope is about 4 stories tall, and the main structure here is about the size of a basketball court. So it is massively huge. The size of a telescope mirror is really important because the bigger the mirror is, the more light it can collect, and the sharper of an image you can see. You all are astronomy enthusiasts, so you probably already know this. But so we're building this telescope to be so big so that it can basically stare further back into the universe, see more distant things, and see things in better resolution. So the first big difference in Hubble and Webb is the size. The second big difference is the kind of light that Webb will see. So Hubble is mainly an optical telescope, a visible telescope that your eyes can see. Webb is an infrared telescope. Oops, sorry. So Webb will see the universe primarily, or all in infrared light, so near infrared out to mid-infrared. And we're designing it that way completely due to the science questions. So back a few years ago, astronomers got together and said, what are the biggest science questions today in astronomy? And they lined out those questions, And the answer to how do we answer those questions is a huge infrared observatory in space. So that's why we're building Webb to be an infrared observatory. And the third big difference is the place in space that Webb will be. So Hubble orbits the Earth about 350 miles up. We're going to put Webb out at about 1 million miles away. And that is so that it can get very, very cold. Since Webb is an infrared telescope, infrared light, you can kind of think of it like heat radiation. So in order for the telescope itself to not be warm and to glow, so it sees itself basically, we are putting it out into deep space so it gets very cold, and so it can observe the faint infrared signals from the distant universe. So the telescope is so big that it's obviously bigger than any rocket that we have, so we have to fold it up and it deploys in the launch. We're launching on a French rocket, therefore the French countdown. So we're launching on an Ariane 5 rocket from ESA, and rocket launches are always awesome, so you have to put one in there. This obviously is an older launch, right? We haven't launched yet. I haven't mentioned that yet, but we're launching in 2018. So we fold the telescope up, and it sits in this stowed configuration here. And so on the next slide, so we'll skip the loud launch. So you see how it starts up, all folded up, like origami. And then once we launch it into space, it starts this really, really complex deployment sequence that you see going on here. So this sequence, as you can see it unfolding, incredibly difficult, right? So I'm a scientist. I can't wait for the data to come back from this telescope. But the engineering behind this machine completely blows my mind. This is hard. But you know, we have the best engineers in the world working on this. And this is going to be amazing. The engineering behind this just is really incredible. So what you see here, some of the parts of the telescope, this main silver structure here is a sun shield. So once it's in space, the sun will always be on this side of the telescope. And of course, the gold structure is the mirror, which will always be looking out into deep space. So as you watch the deployment go through, there goes the secondary mirror. And then the side wings of the mirrors pop out, and then you have a complete telescope in space, like a giant transformer. So that's the engineering of the telescope. So I want to tell you a little bit about the science we're going to do. We have 4 main science themes. First of all, we're going to study the very first galaxies to form in the universe. So with Hubble, we can only see back so far. With Webb, we're going to push back and see the very first galaxies that formed after the Big Bang. So right now we can't see that part of the universe at all. We completely are missing that first epoch of galaxy formation. But with Webb, we'll be able to lift the veil and see those first galaxies that are formed. The second big science theme, I'll skip this movie, I don't want to run out of time here. So the second big science theme we have is, oh no, it's not going to let me skip. All right, we'll watch the pretty movie. Okay. Pretty movie. Okay, so what you're seeing here is a simulation of how we think galaxies formed in the early universe. This isn't real data, this is a computer simulation. And so what we think happened back then was that galaxies started to come together in this sort of cosmic web and started to form big structures early on in the universe. We can't see those first galaxies at all, but with Webb we will be able to. The second big science theme is learning how galaxies grow over time. So when you look at that image of the Hubble Ultra Deep Field, when you see the very distant galaxies, you notice that they don't look anything like galaxies in the nearby universe that we know of today. So that process of how you go from those sort of small, clumpy, unformed things to the large, organized structures is still a very open question in astronomy. We don't know a lot about how that process happened. So Webb is going to allow us to learn a lot more about that process. So this question of how we go from these tiny red dots, which are the most distant things we can see with Hubble, to the large, huge galaxies with, you know, hundreds of billions of stars, still an open question. There's a lot about that we don't know. What we do know is that galaxies come together and collide, and I've already shown you some Hubble image examples of that. And so we think that this process is actually really critical to how galaxies grow over time. So and again, this is a simulation, not real galaxies. This takes billions of years to happen. So unfortunately, we can't watch it in real time. But what we can do is use real physics to simulate how this happens, and we do that. So I'm an observational astronomer. I use data from telescopes like Hubble and telescopes on the ground. But we have a whole group of astronomers that do theoretical astrophysics and use physics. Yay! I have some in the audience. I love it. And so we observationalists work with the theorists most of the time, right? We're usually pretty happy collaborations. And we use what the theorists tell us they think are happening, and we give them the data, and so we work back and forth to figure out the real picture of what's going on in the universe. Is that a good description? Theoretical astrophysics back there? Yeah? Okay, cool. All right. So that's the second big theme. The third big science theme that we have is learning how stars are born. So stars are the building blocks of galaxies, but there's a lot we don't know yet about how stars are born. And that's because stars are born inside these dust clouds, and so they're hidden from our view. One cool trick of infrared light, so this is visible light, and in a second it's going to fade to infrared, and what do you see? You see the star pop out, right? So this is going to be the capability that Webb's going to bring us. This is the Hubble image. So after the last servicing mission, Hubble has a little tiny bit of capability in the near infrared. So with Webb, we're going to expand on that and be able to learn a lot more about the process of star formation. And then the fourth big science theme, there we go, is learning about alien atmospheres. Yes, really, okay? So this, for me, is one of the most exciting things about this telescope. So I study distant galaxies, right? That's my area. That's what I study for a living as an astronomer. But for me, this science is going to be the coolest stuff that Webb does. So now we know, thanks mainly to the Kepler telescope, that we know now that there are thousands of exoplanet candidates, so planets orbiting other stars. We know that they're out there, but we don't really know a lot about them. So now that we've had Kepler for a few years, after studying a little patch of sky and learning about these stars, we now know that there are probably more planets in the universe than there are stars. We know that planets are common, and that's something that wasn't known even 5 years ago. And so anytime at night you go up and you look up at a star, you point at a star in the sky, it probably has a solar system around it, right? That's amazing. That's something that we've just learned recently. But even though we know that they're there, there's a lot that we don't know about them. And so what Webb is going to do is allow us to really learn about the atmospheres of these exoplanets. So this is a picture from one of NASA's solar observatories that shows the transit of Venus in front of the sun. And what you can hardly even see here is that Venus has this teeny tiny little thin atmosphere. And so it's in front of this gigantic bright star. So this shows you how hard this is. So we're trying to see the atmosphere and the glare of these bright, bright stars. Really hard to do, but Webb is going to be able to do it. Webb will have the capability, for example, to detect water vapor in atmospheres of some of these exoplanets. You can start to think about where that's going to take us, right? Webb is the next big step on our search for life in the universe. Really cool science. The good news is we're building it right now. So I'm just going to take you through some imagery of some of the awesome hardware that we have. This is 6 mirrors. We have 18 mirrors total on the telescope. All of the mirrors are done now. They've all been delivered to NASA Goddard, where I work, in these space-agey looking pods. These are really mirrors. There aren't aliens in there, right? People always think, that looks like there's an alien in there. But we have all 18 of these mirror segments at Goddard now. They'll be integrated and put onto the telescope structure next year. So this is the backplane structure. This is the huge structure. And here are people for scale, right? The thing is very big. And we've been doing some tests recently at Goddard where we're practicing how to place test mirrors down on the backplane. We have a phenomenal photographer on our program at Goddard that makes these hardware, takes the hardware and makes it beautiful. I think it's fantastic. This is a test article of the huge sun shield, about a basketball court-sized sun shield that we're building. 5 layers thick, has to fold up. Amazing technology here. They carry things around for this telescope in a C-5 aircraft, which is awesome. In addition to, I'm also a pilot, and so airplanes, I love airplanes. So anything that combines astronomy and airplanes, all about it. Love this, so cool. So yeah, we ship parts of the telescope, barely fits inside C-5, the biggest military aircraft that we have. We're building these instruments at Goddard now. We have 4 science instruments. All 4 have been built. All 4 have been tested and integrated together onto a big structure. Our this is our integrated science instrument module structure, which is a mouthful, but this is basically the structure that all the instruments get put onto. And here's a picture of one of the instruments being integrated onto that structure. This is at the gigantic clean room at NASA Goddard in Maryland. All right, we do lots of really, of course, extreme testing in extreme environments because this telescope has to live in the cold of space. This is inside a huge thermal vacuum chamber at Goddard. Another picture from inside that chamber. This is a test structure that we mount things on to test them. And then a look upward from the bottom of this structure. So we are making really great progress on the hardware. We have all the hardware basically built. So for the next 3 years, we're putting the pieces together and testing and testing and testing again, and because we can't go fix it. And so that's where we are with the telescope. Really excited. And so thank you guys for listening tonight.